Hi everybody, welcome back to the last part on Multirate Signal Processing. So this part will be about the implementation of neural networks using Python Pytorch. So far we saw the implementation mainly with Keras, but Pytorch is an alternative to Keras. Pytorch is used when more control of the neural network structure is desired, or if a more general use of print for debugging purposes is desired. So this is actually what I like a lot. I like to use prints for debugging even inside the neural network model, and that helps a lot for debugging. So that's convenient. You can download Pytorch from its website, so that's different from Keras. You can install Keras using PIP, but for Pytorch you have to go to this website, pytorch.org, and get started locally. But it's fairly easy. So in this on this page you have quite easy instructions, and you just follow the instructions using the settings for PIP, Python, and for CUDA none if you don't have a graphics card. So that will be working, I guess, most of the time. So our example for convolutional neural network with causal padding corresponding to Keras simple convnet.py can be executed with Pytorch symbol convnet. So I can open this here. So let's go to our terminal shell, gedit, and then open this. And here you can now see how this simple convolutional network looks like in the case of Pytorch. So basically it's quite simple, except here in the beginning you import torch or torch.nn for neural network. Then here you generate the dummy data, the test data. So here we have our test signal, which is this ramp function, goes up and then goes down. In the beginning you have 9 zeros, in the end you have 9 zeros. And you want to do the detection using a convolutional neural network. Here you have the target function for the desired output. So here we have a 1 at the time of detection and zeros everywhere else. And here we bring it into the desired dimension. So here we have then the main part of our execution of the program. So here we have first the dummy data, which we turn into corresponding torch tensor. Then we define the model, and the model here is consisting of Pytorch neural network, sequential model you can see here. So this is the type for a sequential neural network, and here in the argument you can see the components of this network. In this case it's just one layer consisting of this convolutional layer. So here you can see it has this conv1d, and here you define the dimension. So here in channels we have just one channel, out channels again just one, kernel size, which corresponds to the filter length, is 8, stride, which was the downsampling rate, was 1. Here the padding, so this is slightly different from Keras. In Keras, remember, you had different types like causal or full or same. Here you can define the number of zeros padded on each side, the beginning and the end of your signal. So here you can see padding equals 7, which is actually kernel size minus 1. So this gives you the full output. So after defining the model in this way, you define the loss function, mean squared error loss, and then the optimizer. Here you can see we define the optimizer. and this optimizer works on the model parameters. Then here we have now the optimization loop. So this is also different from Keras. Remember in Keras we had the compile statement, and here we have a for loop. So here we define a for loop, and here this is the number of iterations or epochs. And here you can see the individual optimizer steps. So for each loop step, it computes the output of the model. So here, given the input, which we just defined, it produces the output. And then we can compute the loss function based on the target function and the computed output signal. This is the loss. And then we can take this loss function and compute the gradient, starting with zeroing the previous gradient in this step here, zero grad is zeroing out the gradient from the previous step. Then it takes the loss and does the back propagation, and here in optimizer step it updates the weights accordingly, according to the gradient and the backward propagation that we just did. So here, instead of having just one line as in Keras, you have several lines, but this also has the advantage that you have more control over what's going on. For instance, you could just get rid of this zero grad, and then you have, for instance, a smoothing of the gradients during the update. Or you could have some more computation for the loss function. So the loss function does not need to be one line here. You can actually add more lines to the computation of the loss function. So in that sense, it's actually convenient and gives you somewhat more control. So other than that, it's basically doing the same as in Keras before. So after we're done with a loop for the epochs, for the optimization, we now have our optimized model, the trained model. Here we get the predicted output for the trained model. Here we convert it into a NumPy data, NumPy array, and here we extract the weights. So here model parameters. You see this is the same that the optimizer worked on. So here we extract them and convert it to a list. Here we have the weights, and here we turn it into a NumPy array. Here we save it. Here we save the state dictionary of our model, which contains the weights and more. And here we actually store the weights in the weight file. So the NumPy converted array we can now use to plot. So we apply matplotlib here to plot the weights as usual as before in Keras, to check out the result, the weights and the predicted values. Right. So simple enough. So we can simply execute it here. So take this file and execute it with Python 3. Here you can see it was fairly quick, right? We have 5,000 iterations, epochs, and here you can see the final loss function is fairly small, and here you can see the prediction as a printout, and you can also see the corresponding plots. So here again is our input signal as before in the case of Keras. Here is the obtained weights. They're pretty much identical to what we obtained for Keras. And here's the corresponding output, also identical for the case of the full convolution. Right. So here we can see the peak as desired, and then here the slight ripple to the sides. So this is actually what we expect. So that works nicely. And you can see the differences between Keras and Pytorch. Yeah, so we obtained the same weights. In earlier versions of Keras, they appeared time-reversed compared to Pytorch, but it was later made the same as the convention in Pytorch. This is because Pytorch uses correlation instead of convolution for its filtering process. So you can also read more about this here in this web page. So in principle, Pytorch uses correlation for its convolutional layer, and later Keras was adopting the same convention. So be careful which version of Keras you're using, because the later versions have this flipped definition for the convolutional layers. Okay, so next is the implementation using a dense net. So basically we want to take the obtained weights from our optimization, from our training, and implement it using a dense net. Why? Because in audio processing, the conv1d layer is useful when the entire audio signal is in memory. Then the convolution can be seen as shifting the time-reversed impulse response, the weights, along the audio signal to produce the output of the convolution. But when we would like to do real-time audio processing, the audio signal arrives block by block from the sound card, and we should process them as they arrive. And this can be seen as shifting the audio signal along the time-reversed impulse response, the weights. So instead of taking the weights, shifting it along the audio signals, we now have the weights fixed and shift the audio signal along it. We can implement this using a dense neural network layer, using a Keras dense layer or a Pytorch linear layer. So here they have somewhat different names. This layer has different definitions for the weights and the input, hence we need to translate them for this layer. So we already have our weights from the training, right? The training of the convolutional neural network, the convolutional layer, and we want to reuse them now for our dense network. The dense or linear layer basically implements a matrix multiplication where the input signal is a row vector from the left and the matrix from the right contains the weights. In our case, this matrix is just a column vector, right? Because it's basically a convolution. First, the vector for the dense layer, they don't have the channel dimension, hence we need to remove it. So here, remember, for the convolution layer we have the channel dimension. For the dense layer there is no channel dimension, so we get rid of it by setting this corresponding channel dimension to index 0. So this dimension then disappears here. So then we need to apply the time reversal from the convolution to it, but actually in the newer Keras version, higher 2.4.3 or 2.4.3 and higher, this is no longer necessary. So we could flip it for the lower versions. And then we can set up a dense neural network model. So here you can see it. Filter length is the length of the weights. Then the model here is sequential, as we just saw. Here in this case, I'm not using the argument of sequential, but I'm using model add. So that's also possible. So you can see I add a dense layer. So here you can see this dense is from Keras. So I'm using 1 unit. Activation is linear. So there's no activation function in this case because we just have a convolution. Bias, there's also no bias. And the input shape here corresponds to the filter length. So basically this is the size of our matrix. Right, and then we set it with obtained weights. Yeah, finally we need to transpose the input to be a row vector, which we do here, transposing the corresponding dimensions. And then we can loop over the signal. here it still comes from the signal in memory basically, but it could also come from the sound card. So here is this for loop which goes over the blocks of our signal, which you can see here. So here I'm making the blocks. Here it comes from our data in memory in this case, but for real-time processing this would come then from the sound card. And then you apply the model to this block. Yeah, and we can also let the program run, the coding program. So let me first open it, copy, gedit. So here's the corresponding program. So you can see we are using Keras here, Keras library or Keras module, and the beginning here is the same for everything. Then we import the simple convnet, the generate dummy data function, and here we open the file for the weights that we obtain from the training. Here we do the conversion of the weights from the convolutional layer to the dense layer, as we just saw. Right here we remove the channels dimension. Here we extract the filter length, and here we make the neural network for the dense layer, right, as we just saw. Here we generate the data as before, same data, and here we compute well, not computing yet. We are setting up, we initialize the prediction tensor in this way. Here we do the same for the input data, the ramp data. Basically we set up the transposed version to it, which is needed for our dense network. And here is now the processing for loop. So here you can see, here I'm extracting the blocks. Each block is put into our model for the prediction of the output, and then for each loop here we get an extra sample, and then we can finally predict it, which you can see then if I let it run. So Python 3. So here you can see the output as expected. So here we have this peak at the end of the ramp function, and here those little wiggles before. So that works. So here, instead of using a conv network, we use a dense network and shift the signal along. So next, the real-time online implementation of convolutional neural networks. For a Keras convolutional network, it is assumed that the entire data is already in memory, but in real-time online processing, for instance, for real-time audio or wireless processing, it needs to be processed as data arrives, sample or block-wise. Instead of the convnet sliding the window along the samples, here we slide the samples along the filter, implemented using a dense net. For that, we need to convert the weights data format. For our conv1D layer, the weights have the following format. It's an array of an array with the following arguments. So here you can now see how the weights are organized in this kind of tensor or array. So here you can see the first dimension here is just saying if it's filter weights or the bias. Right. For each layer we need a set of biases and also filter weights. So we distinguish here between them using the index 0 or 1. Then next comes the filter length dimension, then the channels or subbands dimension in the previous layer, and then the number of neurons or filters in this layer. Right. So this comes from the convolutional neural network. This is how the weights and biases are organized. Then we have the corresponding weight format for the dense layer. So again, we have a 0 or 1 first to denote if it's a weight or a bias. Then next, we simply have the total number of weights. So it's not structured. We just have, so the total number of weights results from the filter weights, the number of filter weights times the channels, which is the subbands or neurons in the previous layer, partly time reversed, depends on the version, and then also, as another dimension, the neurons or filters in this layer. Right, so here we have fewer dimensions. We also need to observe that the convolution is a correlation with the flipped coefficients, again depending on the version. In our implementation, we choose to keep the order of the weights, but flip the input signal instead. Hence, the weight conversion from 1D to dense is mainly a dimensionality reduction. So here you can see it. Here's the weights, and here you can see we get rid of the channels dimension. The signal is input into the shifting buffer such that it appears flipped in time, meaning the latest sample appears at index 0. So here you can see it. So here we have our signal block, which is shifted up. So each time a new sample arrives, we have our signal block shifting up one sample, and then we assign the latest sample to the bottom of our signal block, which you can see here. So here's the sample index, the latest sample, which is assigned to the bottom of the signal block. And our example program reads in the weights from the training of Keras simple convnet.py from the convnet weights.pickle, and then converts it. And we can see it here. So let me open it. Gedit. So here you can see it. We have again Keras as a module. We read in import pickle, then we define our signal, we define our model here. We can see it using a sequential structure and a dense layer, again with one unit, linear activation, meaning no nonlinearity, and no bias. And we have the input corresponding to the filter length. Here we have our test data, which is the ramp data, and here we have our main part of the program. Here it reads in the weights which we obtained from training, from the convolutional layer. Here we do the conversion of the weights. We remove the channels dimension here. Here we do the flipping. So here, this is for Keras version larger than 2.4.3. And we need to flip it here because we also flip the signal in this case. Yeah, then we generate the model here and set the corresponding weights. Here we generate the data, and then we initialize the signals first with zeros, and then we have here our for loop for our processing. And here you can see we read in is the samples sample-wise, and insert them into our signal block, and then we apply our model to each signal block in this for loop, and for each time this for loop is executed we get another predicted value here, and finally we can see the output. So let's take a look. Yeah, so here you can see it shows you the prediction shape each time it generates an output. Finally, we have 23 values. Here's the input signal as before. Here's the weights which we read in, and here's the corresponding output. So it actually indeed looks the same as before. Okay, so observe we get the identical output as from our ConvNet, but now we get one output sample for each new input sample from this program. Yeah, and that's it for this part, and this was the final part of it. So thanks for your attention, and then yeah, good success. Goodbye.